So today it has been, the topic is image resizing, but actually the topic is not that, but it's image interpolation. Okay, so let's say that we have an image. We have an image. I use only 3 pixels in each direction. And then we will construct a new image J. That will be, for instance, I minus, so this is equal to I minus I. Okay, so let's say that this is a vector that is just 0.5. This is 0.50. So that means that we have to move the image half a pixel from its current position to the right. So this is J, and then this pixel here does not come from this location, but from the location, but from this one. And this one comes from this one. But we don't know the images at those red locations. No the images. No, chica, mata. Okay, so we don't know the images at these red locations, but we know them at the blue locations. So, for instance, this one is a little bit more complicated, but these two, so for instance, let's say that we are focusing in this one. So, if this one is in the middle between these two blue samples, and let's say that this sample is, I don't know, just to put this in a, this is 10, this is 20. So this one should be somewhere 15 inside. Okay, so how that operation that we have done, that is inventing a value for a pixel that we don't have, for a location that we don't have, is called interpolation. So that operation is called interpolation. And we will learn different ways of doing this interpolation. And this applies to shifts, but it also applies to image rotation. So image rotation is something like this. So an image rotation is transformation like this, where these is a rotation matrix. This is a rotation matrix. So this is equal to, let's say, cosine theta, sine theta, minus sine theta, cosine theta. It also applies to scaling transformations, that is the topic of today. So let's say that these is equal to these three. So we have a scaling factor in x and a scaling factor in y. And then we would have a scaling of the images. And there are many other transformations, and in general, this can be an arbitrary transformation. So this can be R11, R12, R21, R22. So it can be any arbitrary transformation. These are special cases in which this is a rotation, this is a scaling. This is called, in general, this is called affine. And these ones, this kind of transformations also, they are translations or shifts. Okay, so let us see some examples. So normally I use equal at the end. Today I will do it at the beginning. So let's say that we are given this image.
we are given an interpolator, and this interpolator will have a parameter. And look at this parameter. This parameter is the degree of the polynomial that we are using to interpolate. So maybe it's an interpolation. Bueno, contarnos un chiste, anda. ¿Cómo no vayas a saber chiste?
Yo te puedo contar el mismo siempre. Lo mismo.
Bueno, pues cuéntalo.
Te lo cuento otra vez.
Claro.
Vas por la carretera y ves un cartel y te pone aceros inoxidables. Y te dice, no los hacemos.
Bueno, Verónica.
Van dos y se cae el medio.
Okay, so this is the degree of the polynomial that will be used to interpolate. So when I did this interpolation, so we said that the pixel at this point is 10, the pixel at this point is 20, so the one in the middle is 15. So what I'm doing is using an interpolation of degree 1. So what I'm doing is forward. So I'm taking, okay, so let's use the right colors. So I have here n, so just to show in this direction, let me use instead of n, I will use x. So this is I of x0. So I'm just plotting the first column, and then we are saying, okay, so at 0 is 10, at 1 it is 20, and then at 0.5, what I'm doing is joining this by a line. And a line is a polynomial of degree 1, and then I'm taking this at 0.5, and this takes the value 15, so the value between. But this polynomial here is a polynomial of degree 1, so it is of the form the image is ax plus b. So it is degree 1 in the coordinates. Okay. Okay, so are there differences? There are. So here we can choose the polynomial. So I ran this example with polynomial of degree 3, and here is the transformation. So the transformation is moving a little bit the borders, so we can see that this is the input image and this is the output, and what we have done is to shift a little bit the corners of this image. And here what we can check is this is the input, this is the interpolation with degree 0. So you see that it is not as simple as a simple shift. That is the degradation of the quality. And again, between bilinear and sorry, this is bilinear, and so this is degree 0, this is degree 1. So you see there are differences. And between degree 1 and degree 3, there are differences, but they are less noticeable. Okay. So, okay, so let's learn that. Okay, so we go here. Okay, so here we have same representation of this idea that you have an original image and then you change the size. So you make, in general, all these transformations are called geometric transformations. And then, depending on the way you interpolate, you have more or less quality. So here is the 0 order polynomial. This is first order polynomial. This is third order polynomial. And what you see is that this one preserves much better the details of the original image. And this is expected. So if you do a Taylor expansion of a function, so the higher the degree of the Taylor expansion, of the polynomial of the Taylor expansion, the more details you keep. Okay, so So let's say that we want to, so we will start with zero order interpolation. So with zero order interpolation, so let's say that we have this image and we want to enlarge it by a factor of 4. So this is one of these operations that we represented the other day. So we have an image. So we have an image. Image goes outside. Image goes outside. We are doing an upsampling by a factor of 4, and this operation, the way it is defined, it is like this on different color. Here, for instance. So what we are saying is this I prime. So I prime. I will do it in 1D, okay? But it applies in both directions. So I prime n is I n divided by 4. The n is call it n prime. So just to highlight that this is the axis of I prime. If I prime is a multiple of 4, and then 0 otherwise. Okay, so these would have the values of the image plus a lot of zeros. And then this is not a very good representation of our image. So what we normally do is to apply a filter. So now we can wall with some filter just to fill the gaps. Okay, so this is here. So we start this image, it's the upsampling. So it has a lot of zeros in between. So it has a value, then a lot of zeros, then a value, a lot of zeros, and so on. Now we have to fill the gaps. And to fill the gaps, one possibility, okay, so this is a sum of that thing. So a possibility is, these are the values that we have. So why don't we simply copy those values to the nearby pixels? And if this is our gap filling operation, this is a filter. This one here, this one here, is simply a matrix full of ones. So this one is copying the pixel to the nearby, to the neighbors. Okay, so this is a possibility. This is called nearest neighbor interpolation. Okay, and then we can do the opposite. So we can start with a big image and produce a small one. And this operation we already know. It's called the decimation. This. So represent it like this. So we start with an image, and then we do a downsampling here by a factor of 4, for instance. And again, our image here, I prime at n prime is I for n. So this is our operation. Yeah, so if we want to do it, this is 1D. If we want to do it into D, so I will do it as here. So if I want to do it into D, then this is a vector, and then this is a factor. Okay, good. So this is the decimation. This is very simple. Okay, you simply have to go 1 every 4 pixels and then simply copy whatever is there. And then you produce a new image. Okay, so this way of sampling, it is called nearest neighbor interpolation. Okay, so let's see. Let's say that yeah, with factors that are integer factors. So we did a downsampling or a decimation by a factor 4. We did an upsampling by a factor 4. So if this factor is an integer number, then this is very easy. What happens if it is a fractional number? What if it is 3/7? So then it is not so simple. So, but we can do something similar. So what we can do, let's say that we want to do a resizing by a factor 3/7. So what you can do is to divide the original image into blocks of 7 times 7, and then you have to take 3 pixels out of those blocks. So this could be a possibility. So to take all these factors. That's it. There is a drawback here, that is the sampling is not uniform anymore. So the distance between one pixel and the next, sometimes it is 2. So let's say that the pixel size is 1. So sometimes it is 2, like in here, but sometimes it is 3. So this non-uniform sampling is something unpleasant. And we will fix it later with the bilinear interpolation. Okay, so now you simply have to copy those pixels. Then you put them together and you produce a new image. And here you have a detailed, what is it? Yeah, detailed of the resized image and detailed. Okay, so now let's do the opposite. So we want to upsample, but now by a non-integer factor, so 7/3. 7/3 means that I think there is a good presentation. That was okay, but it is simple. So we can go to here. I can reuse this. Okay, so we have to do the opposite. So I have to take blocks of 7 times 7, but now in the output image, and I have to fill 3 pixels from the original, and the remaining I have to fill the gaps. Okay. So I can do that. So this is the upsampling. So you take blocks in the output of 7 times 7, you copy 3 of the pixels from the original, and then you have to fill the gaps. And the gap filling can be simply copying the value that you have closest to you. Okay, and now it is time to formalize all that. Okay, so let's try to formalize. Okay, so first thing is, okay, so forget about this R-1 and C-1. That is very small detail thing about what happens if with the borders and so on. So let's take the main idea that is this R divided by R prime. Here it is the same. It is R divided by R prime. That is a small detail of minor one, but let's forget about it.
These both methods of previous movement are for image resizing.
It is for image interpolation. Nearest neighbor is for image interpolation. We are presenting it here for resizing, but I already introduced it at the beginning that we can apply this to any image transformation, geometric transformation. Okay, so let's see. So let's say that we have an original image of size R times C, and we want to produce an image of size R prime C prime. Okay, so let's draw that. Okay, so we have here an image of size R times C. This is image I, and then I want to produce something that is of size R prime C prime, and this will be image J. Okay, there will be a factor. There will be a factor that goes from here to there, and there will be two factors. We will use a matrix R that has a scaling factor in X and then a scaling factor in Y, and these two will be 0. Okay, so what is the scaling factor in X and in which direction they go? So they go in the direction, let us write it in the same way as we have done it here, C divided by C prime. So actually this goes in this direction, you'll see why now. So this factor here, it is R, this is X, so this goes with C. So this goes C divided by C prime, and this one here is R divided by R prime. Okay, so our image J at a given location of J is image I at the location R times Rj. Let's see if that goes correctly. Okay, so this is a coordinate. This is a coordinate in R prime, in R I. Why? Okay, so we are taking a coordinate here. So we are taking a coordinate here, and for that coordinate, what we are seeing is where this is coming from. This is coming from this location. Okay, so let's see. Let's say we are doing it just to put this in numbers. So we are doing a downsampling by a factor 2. Okay, so we are doing a downsampling by a factor 2. So this is twice this one. So this is 2. This is 2. This is 2. Okay, so our matrix is 2, 2, 0, 0. Okay, now I take the coordinate. I will write now a table. This is good color. I will write now table Rj I. Now I take the value, I coordinate 0, 0. Where is it coming from? I have to multiply by that matrix, so that is coming from 0, 0. Now I have 0, 1. So 0, 1 is coming from 0, 2. And 1, 0 is coming from 2, 2. And 1, 1 is coming, this is 2, 0. And 1, 1 is coming from 2, 2. And 1, 2 is coming from 2, 4. So I don't have to write all. Okay, but you take the idea. So given any location at Rj, I simply have to multiply by this matrix and I will have the coordinate. Okay, so what if my matrix is 2, 2 is very easy to write, but I can have arbitrary matrices. So I can have one that is 7, 3, 0, 0, 7, 3, as we had on the slides. Or I can have the opposite. So I can have 1, 2, 3, 7, 0, 0, 3, 7. So this one, so all these matrices that have factor, so if the scaling factor, so if the scaling factor is larger than 1, and what I'm doing is a reduction. If the scaling factor is smaller than 1, what I'm doing is a zoom. Zoom in. This is also called zoom out. Zoom out. And this is a larger body, so let's do. So
this is reduction, this is enlarging, this is zooming. Okay, good. Okay, so that is what we have there. So we have the scaling factors, we have the matrix multiplication, so the image, so the coordinate, you start at the coordinate from the J image, R prime, C prime, you multiply by your matrix, and then you have the fractional coordinate from which you have to copy that value. So if our image is so if our transformation is of this size, so let's say that I want to transform a coordinate Rj, so I have the coordinate xj, yj, I multiply by this matrix, 3, 7, 0, 0, 3, 7. So the coordinate in the original image is 3, 7, xj, 3, 7, yj. But in general, this is not an integer value. So it is only integer for xj, yj's that are multiples of 7. Otherwise, it is a fractional coordinate. So that means that I have to interpolate my image at some non-integer location. Here. So that means that I'm here in the middle, and then I have to copy from somewhere. Okay, so what is the nearest neighbor? Nearest neighbor is the simplest solution that we can have. So let's say I have this, I don't know, for xj, 3 over 7 is something like 0.4. Okay, so let's say that I have the values. This is rj and ri. Okay, so let's say I have 20. See, just to focus on one of the coordinates. So I have to copy from 20 times 3 over 7. And this 23 over 7 is somewhere, something like 0.9. 0.9? 9 point something. Yeah? This is 8.7, let's say, 8.7. So what can I do? I can choose the nearest neighbor. So what is the nearest neighbor? I have to round it up to 9. So in general, my coordinates will not be these ones, but this one rounded. Okay. So yeah, this is a notation that is very much used. So we have x. So this is round of x. If you want to round down, put it like this. So round down of x. It's also called log of x. And you have this one, this round up of x. And this is also called ceiling of x. Okay, so for instance, here, if you have 0.8, so 0.8 rounding is 1. If you round down, 0.8 is 0. And if you round up, this is 1. Okay, so
nearest neighbor is this one. Nearest neighbor is this one. Okay, so you take the coordinate. Take the coordinate and then you round. Okay, so what you have there. So you have the fractional coordinate, and then you have to copy from the I at the rounded coordinates. Okay, any questions so far? No? Okay, so all this is just small comments on these ideas. We have all kind of representations of these kind of things. The idea is all the time the same. And so sometimes you are in a location where you have data, like here, you are in the middle of the pixels, and most often you are not, you don't have. So you will have to round it to the closest point that you have. Okay, so this is nearest neighbor interpolation. So it is a very simple interpolation, but as we have seen that, it is not very good. Okay, so I'm skipping all these. There are small details that we are not interested in now. The next interesting idea, so this replication is associated to nearest neighbor interpolation. Okay, so, but we can do better. So we can do kind of this line interpolation that I did when I was going from 10 to 20, and then in the middle we have 15. So this will be called bilinear interpolation. So, yeah, again, this pixel replication is nearest neighbor, and then you can see the difference when you do bilinear interpolation. So bilinear interpolation, so going very abruptly from black to white, and you're going in discrete steps. And you can go smoothly. Okay, so you can go smoothly from black to white and take all the values in between. Okay, so this, the difference between these two is this one. So here you have kind of stairs, while here you don't have stairs. You have a blurred image, and it makes sense because we don't have enough information. We are going from something small to something big, and we don't have the information in between, so we have to invent it. So it is normal that we have kind of blurred borders, but otherwise we can go smoothly rather than with a step. Okay, so let's see how we can do that. So let's say that you may remember. Let's do it by a factor 2. So if we do it by factor 2, so so we have it here. We have it here. Okay, so my first step will be to do an upsampling by a factor 2 in this case, and then I will have zeros in between. So my output will look like this. So these are the 4 pixels in the input, and then when I put the zeros in between, this will be my output. So my output will have twice the number of pixels, and it has zeros in between because for the moment I don't know how to fill them. Okay, and then I can look at the gray values for the data I have. So here where I have the zeros, I don't have the data, but in the corners I have the intensity values from the original image. And then what I can do is to expand this idea of fitting a line, but now to 2 dimensions. So in 2 dimensions, instead of fitting a line, what I can do is fit in a plane. So I can fit a plane. There is only one plane that goes through all those values. And then if I need this value here, what I do is just to interpolate the plane or to evaluate the plane at that location. And the same for all the others. So I fit a plane, and then I can get this value, but also all the other 0 values that I was missing. And there is only one plane that goes through all these 4 pixels. How do we know that we have only one plane? Okay, so let's think of that. So let's go here. Okay, so we have X, Y, we have the intensity, and we have a plane. Okay, so a plane in that intensity space is this 3-dimensional space. It's written like this. It is A, X plus B, Y, C, I, plus D equals 0. How many parameters do we have? 1, 2, 3, and 4. These are the coefficients that define the plane. So I just need 4 values. So I need 4 parameters, and if I have 4 coordinates, so if I have, let's say, so I have these 4 values that belong to the plane. This patch belongs to the plane. So there is only one plane that goes through all these 4 values. So if you have 4 intensity values, and you have 4 parameters to determine, there is only one solution for that problem. Okay, so this will be the result. So the result is we know from the original image, we know these 4 corners. Now, we fit the plane, we evaluate the values in between, and then we have the smooth transitions. So these 4 corners are given from the original image, and all the others, they have been interpolated. So, and if you look at the line, so for instance, let's say that this is, I don't know, 10, this is 20, this is 15. So it is, if you look at the line here is a straight line. So it is the same linear interpolation that we were doing before. It is a first order interpolation. We can also look at, and also recognize that here. So this is a polynomial in X, Y. It's a polynomial of degree 1. So it is a line. So if you look at, if you fix Y, I depends linearly on X. So this is a line, this is another line, this is another line. Then, so we'll take this image and enlarge it by a factor of 4 and compare bilinear and nearest neighbor. Okay, so this is a bilinear interpolation. Sorry, this is nearest neighbor, I think. Okay, so we first do the upsampling. And this is the result with replication. So this is nearest neighbor, and this is the result if you do a bilinear interpolation. You can compare these two. So one is going in steps, the other one is going smoothly. And what else? Yeah, so here we have the results with bilinear interpolation and nearest neighbor interpolation. And this one is much better. You see the borders are much smoother than here. We have here a lot of steps. This is the same. So, yeah, that is an interesting idea now, here with the bilinear interpolation. So here we are comparing the locations that we are copying when we apply nearest neighbor interpolation to the ones where we apply bilinear interpolation. So this is the 0, 0. So 0, 0 is the same for bilinear and nearest neighbor. But then the next one for nearest neighbor is this yellow one. And then the next one is this yellow one. So they had this problem that we were having steps of size 2, and sometimes we were having steps of size 3. But now our step is all the time 7 divided by 3. So if it is 7 divided by 3, we have to take the value from this location, which we don't have it. We will have to interpolate. And then from this other location, and then from this other location. But the steps between, the distance between pixels is all the time 7 divided by 3, all the time. So now we have a uniform sampling. Okay, so then, yeah, so let's look at that section. So these are the locations from where we have to take the values. Okay. And we will fit a plane, but there is a very simple way of fitting a plane that we will see now. This is the following. Okay, so these are the pixel values that we know. Okay, so these are the pixel values from the Okay, now let's move to there. So here it happens that the pixel value that we need, that is this red one, is one of the pixel values that we have at the input. So we simply copy it. We don't have to interpolate anything. But now we move to the next one, and we need the value there. We need the value there, but we don't have it. All we have is these white values here. So we have to evaluate, so we have to fit this plane that goes to all these 4 corners, and then evaluate it here. And the same happens there. Okay, so yeah, so this is this showing. I think it is more interesting this one. Okay, so we have these 4 values. Okay? These are coming from the input image, and we want to evaluate it here at a fractional location. So the recipe is this one. So this is the recipe. So let's take it. Let's do it here on the Y. So I have 4 corners. I have these 4 corners. But I know the values. So this is RC. This is RC plus 1. This is R plus 1C, R plus 1C, and this is R plus 1, C plus 1. Okay? Now I need the value here. So what I will do is to measure the distance, between this coordinate, that is this R fractional, C fractional, and say, okay, that is a delta R here, and that is a delta C here. And then the output at the location R prime, Rj, Cj, that I have to copy from this R fractional, C fractional will be. Okay, so let's write it and we'll make the break. So will be I RC times something. So times what? It will be times 1 minus delta R, 1 minus delta C. Okay, I add C plus 1, and then this will be 1 minus delta R, delta C. I R plus 1C times delta R, 1 minus delta C. And I R plus 1C plus 1 delta R delta, sorry, delta C. And after the break, we will see why. So we are taking these four values that we know. Let me use a different color. These four values that we know. There will be these four values here. And then we are using the weights, the distance to those points. We are using them as weights. And we will see that that is a plane and why those weights. Okay, so let's make a break. 10 minutes. Okay, so there is an interesting question. That is, how do I know which are the 4 pixels that I have to copy? Okay, so let's say that at some point you want to evaluate let's say I at 29.7 and 7.2. So which are my 4 colors? So this will be 29.7. So this will be 29.7. This will be 29. Oh, this is 37. This will be 29.8, and this is 38. So it is given by the location you want to interpolate. So once you know the fractional location, simply you have to take the one before and the one after in each direction. Okay. And then this plot, so for instance, 29.7 to 7.2. This is, let me do it right. This is here. This is here. Okay. So we have 0.7 in this direction, 0.2 in this direction. Okay, so we are here. So how do we know that this formula is giving us a good rate? So I have copied again the same diagram that we had before. I have copied the formula, the interpolation formula 4 times. And then let's see. Okay, so let's look at, let's say that we want to interpolate this value here. So this value here has delta equal delta C equals 0. So that means that this term goes away because it has delta C and delta R. This term goes away, this one goes away, and this one is 1, this one is 1. So this pixel is this one, as it should. Okay, let's look at this one. So that one, let me use a different color. Let me use this one. So this one here has delta C equal 1, delta R equal 0. So this one goes because it has delta R. This one goes because it has delta R. And there must be another one. Okay, now we have delta C equal 1. So delta C equal 1 means that 1 minus delta C is 0. So this one also goes. And then these two, this is 1, this is 1. So this pixel here is this one, as it should again. Let's look at another one, the last one. This color. Then here we have delta R equal delta C equal 1. So that means that these terms goes because delta R and delta C are 1, and then these terms are 0. This goes, this goes. This is 1, this is 1. So this pixel here is equal to this pixel. So it seems that it has the right structure. And you may expand it, and you will see that it is a plane. Okay, so it seems that it is not. But why does it seem that it is not a plane? Which are my coordinates in which I should be linear. So let's copy this again. I'll put it here. So this should look like a plane. So my coordinates are these two. So are delta C. So these are my x and y. When I was doing before this presentation, when I was saying this is x, this is y. Now x and y are represented by delta C, delta R. Okay, and then I have the intensity. And I'm working all the time in the region 0, 1. So this is the region 0, 1, 0, 1. So delta and delta C are only taking values here. And then I have the 4 values of my intensities. Okay, these are the red values that we are having from our input image. So this goes here. I have a plane going through those 4 points. Does it look like a plane? This formula here, does it look like a plane or it doesn't? No. Why not? Who said no? You? Why it doesn't look like a plane? Because in a plane, it is right here. Because in a plane, I should have something like this. I should have A delta R plus B delta C plus C I plus B equals 0. So my terms should always be of degree 1. And here I have, it seems that I have terms of degree 2. This is a term of degree 2. I have the product of the terms. So, and all the time, it seems that we are having products. But actually, you can expand this thing. So you can expand that thing. You can be very patient about this. So we have RC times 1, 1, okay, minus delta R I RC, and this is delta R times 1. Okay, then I have also minus delta C I RC. And then I also have IRC delta R delta C. Plus IRC delta C. So these are the terms. These are the terms that are studied. But if you make the full expansion at the end, all these terms disappear. So it is a plane. Okay, Then, this one. Okay, so this is bilinear interpolation. Yeah, this is all the explanation that has been given. And at the end, the scheme is the same. So we are back to these transformations that we were having before. So we have here, you see here. So at the end, this is the general scheme. So the general scheme is the image. So the image J at the location J is, you take that location, you transform it somehow, you have a fractional coordinate Ri that you have to evaluate, the image I you have to evaluate there. So all the geometric transformations, they respond to this structure. And in the particular case of resizing, the matrix looks like this. But in some other transformations, and we will see more in the next lectures. But for some other transformations, still the scheme is the same. So you have a coordinate J, you have to transform it, and then you have to evaluate the image I at that location. So the scheme is all the time the same. And these are called in general geometric transformations. Geometric transformations. And all this is an explanation of all I have said. Okay? And here you have examples of different factors. What happens with colors? Colors are the same. So we have explained this thing with scalar images. So our image is here. Our image is here. They were scalar images, but nothing prevents us from saying this is a vector, this is a vector, this is a vector. And then these are the different weights of these vectors. So we can do now this interpolation with color images. And then what we have to say is we have to take the color vectors from each one of the corners. So we have the color vectors, and then we have to put the right weights. That's it. Okay, so bicubic interpolation. Okay, so we have focused on these 4 pixels here. So we have a fractional pixel here, and then we have taken the 4 nearest neighbors. But we know, let's look at this. You know the Taylor expansion. Let's look at the Taylor expansion. So let's go to some place where we have space. So let's look at the Taylor expansion. So we have a function f of t, and this is f of 0 plus. So let's say that t is close to 0. So it is close to the values that we have. So plus, and then it is f prime of t, evaluated at 0, 1 t plus f second 0 to t squared, so on. This is the Taylor expansion, isn't it? So that means, so let's look at this. So this is, I'm saying, this function is a single order polynomial. So if I stop here, I approximate my function by a single order polynomial, and then by first order polynomial, and then by second order polynomials. So that means that the more polynomials, the higher the degree that that you want to include, the more derivatives you are including. And we know how to estimate derivatives. Okay, so let's say that I want to estimate what is the derivative at 0. So what should I do? So what I have to do, and we have seen this a few times, I can take, let's say that the sampling rate is 1. Okay, so I can take f of 1 minus f of 0 divided by 1. And then let's say that I want to estimate the second derivative. If I want to estimate the second derivative, I have to go a little bit further. So I have to take, now I will not write the exact formula, but it will be a function of f minus 1, f of 0, f of 1. So for first order derivatives, you need two values. Otherwise, if I don't see two values, I cannot tell you how that function is changing. I need two values to see how it is changing. And for the second order, it is how the derivative is changing. So if I have to tell you how the derivative is changing, I need two values of the derivative. So I will take these two values for the derivative and then these two. And then I can tell you how the derivative is changing. So that means that if you take just these four values, I can tell you how the function is changing and how is the derivative of that function. I have one sample, the next one, and then I can estimate derivatives. But if I want to estimate what is the second derivative here, so if I want to tell you what is the second derivative here, I will need the sample on the right and the sample on the left, just to tell you how the derivative is changing. And the same here. So if I want to tell you how the derivative is changing here, I need this value and this value. So now, if we expand our region, not just to these four values, but to these 16 values, I can tell you how the function looks like, so the zero order approximation, how the first order approximation, how the derivative is at that point, and how the second derivative is at that point. Okay, so this is nearest neighbor. Nearest neighbor. This is bilinear interpolation. And this is quadratic interpolation. We don't put B. We can put it B quadratic. So B quadratic, the B comes from two dimensions. So my formula here is one dimension, but you can put it in two dimensions, and then you will have the dependence on x and the dependence on y. It will be the same kind of formula. We have first derivative, second derivatives, and this will be the delta R, delta C. So we do it in two dimensions. This will become delta R squared, and you will have equivalent terms for the delta C. Okay, so we are not restricted to just for values. I have a lot of values there. So I can estimate how the derivatives also change. And then they can have a better formula. And again, we will not go into the details of this one, but the idea of B-cubic interpolation, and now you understand the term B-cubic is that in the Taylor expansion, we have even added an extra term. Okay, so we are doing interpolation of degree 3. So with these four values, 4 times 4 values, you can go up to degree 3. And here you see a little bit the ideas that I was telling you before. So let's say that I want to estimate the derivative. The derivative, for instance, in rho, that is this one. Okay, so I am looking at this value. I want to know what is the derivative here. So I can take one sample and this one, or this one and this one, or I can take these two. Okay, so I can say it is r plus 1 minus I r minus 1, and then divide by 2. Because there is a step of 2. The distance between these two samples is 2, it's not 1. On the same in C, you can estimate what is the second derivative in R and C. And so this is second derivative in R and C, and then you have this formula. So the idea is that if I don't restrict myself to just one point, so one point in the 4 neighbors, but I take a wider neighborhood, I can estimate how the derivatives are changing. And then you can construct a Taylor expansion around that point. And you will have a more accurate representation. And yeah, we will not see the details, the calculation details here of the cubic. But you see that now the polynomials. So what you're saying is the output image is a neighborhood of the input images. So this sum is going over all these pixels. And then it is taking all these pixels with the right weights. And the right weights are given by a polynomial of degree 3. And the bilinear has the same structure, but now with the polynomial of degree 1. But again, why this 4, why this 6, we don't go into those details. Okay, so now we have original image. Now we do nearest neighbor interpolation, and we understand in terms of Taylor expansion. This is an expansion of degree 0, degree 1, degree 3. So this one, we would expect to have lower quality than the other two. And that is really the case. Look at this window here. It has some kind of pattern there that was not existing in the original image. And it doesn't exist when you have cubic interpolation. So, and you already know the name of that pattern. What is that? Aliasing. That is aliasing. So at high frequency, you're mixing up energies. And you're not doing it at the cubic interpolation. And the same happens here. So there is a kind of funny pattern here that doesn't occur when you do cubic interpolation. Again, this is in aliasing. And yeah, you have same images, but now zoom. Okay, so you see the aliasing better. Yeah, now we can enlarge it. So instead of reducing the image, we enlarge it. And here is with nearest neighbor. Now the pattern is not so noticeable because we are not mixing the frequencies anymore. So mixing frequencies happens when you do the decimation, not when you do an upsampling. When you do an upsampling, there is no aliasing. But still, the quality is much better here. So in the cubic, you can look at the small details. So for instance, this flag here, or the small windows. And then those details in the big cubic are a little bit better. Okay? But when you do an upsampling, there is no aliasing. Aliasing only occurs when you do decimation. Well, any question?
linear interpolation, when you compute the value of pixel and then you put all of them together by the signal or you
No, you apply this formula, the bilinear. Linear, you have to apply this formula. So you put the 4 values, and then you give the right weights to each one of the values.
when you have all those pixels, you just put them together
No, you have to evaluate J. So J at this location, you compute this thing, and it will give you a number. That is your new value of J. You don't have to put all these 4 values into a single one. More questions? No more questions? Okay, so otherwise, we go to the exam. So that